Okay, so for today's video, 4.2, we're going to talk about the real zeros of a polynomial, and then the very next video, 4.3, we'll talk about complex zeros of a polynomial. So they'll basically be the same section, but one of them will add a little bit more. It'll take basically any zeros. It doesn't have to be just the real zeros. Okay, so we're just going to kind of think about the fact that f of x can be written as q of x times g of x plus r of x. So if we look at this, formula right here, we have f of x equal to this. Normally we consider r of x the remainder, but let me just show you what it does here. So it says if f of x and g of x are polynomials, then there are unique polynomial functions q of x and r of x such that when you divide, so notice here all I did was I divided each term by g of x. Okay, so we divide that by g of x, and we're left with this plus this, right? So we have f of x divided by g of x, so that's basically long division. We're basically going to take some function and then divide it by another function, in this case a polynomial divided by a part of the polynomial, or a polynomial, another polynomial, and then we want to see what happens. So this is basically the way that the division algorithm works. It's just not actually going through and doing it, but we'll do that. We'll do long division and synthetic division in this section or the next section as well. So we have the remainder theorem. The remainder theorem says let f be a polynomial. If f of x is divided by x minus c, then the remainder is f of c. So this is important. What this is saying is that if f of x is divided by some function, some factor x minus c, then the remainder will be whatever, right? Whatever f of c turned out to be. So let's look at this. It says find the remainder, find the remainder if f of x is equal to x cubed minus 4x squared minus 5, if this is divided by x minus 3. So what we're going to do, we're not going to do long division, we're not going to do synthetic division. We're literally just going to solve this for c. So x minus 3 equals 0, so x equals 3. So then all I do is f of 3. So this would be 3 cubed minus 4 times 9 minus 5. And this would be f of 3 equals what, 27 minus, well, let's do this, I don't want to mess it up. 27 minus 36 minus 5. And I get negative 14. Okay, so that's correct, negative 14. So then that is my remainder, okay? So this is the remainder when you take x minus 3 and divide it into x cubed minus 4x squared minus 5. Let's do the same thing over here. Okay, so you guys have x equals negative 2. Okay, so what I'd like you guys to do now is just pause the video, plug it in, see what you get. Okay, so you unpause it, and we now have, f of negative 2. And you guys should have done this. This would be negative 8 minus 16 minus 5. So we should get negative 29, I believe. And that is now my remainder. Okay? Now these two ideas, or these two problems make us start thinking about something. You know, what does the remainder signify anything? Well, that's the very next theorem. It's called the factor theorem. So a lot of times the remainder theorem and the factor theorem kind of work hand in hand together. So we have the factor theorem. Okay, so the factor theorem says that let f be a polynomial function and then it says then x minus c is a factor of f of x if and only if f of c equals 0. Okay, this is not a typo. This is how I write if and only if. If and only if is powerful because it's a two-way street. It means that let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c is 0. Well, this means two things. This means if f of c equals 0, then x minus c is a factor, right? But it also means going the other way. It also means if x minus c is a factor, then f of c had to be 0, right? So it's a two-way street. So if you know that f of c is 0, then you know that x minus c was a factor. If you know x minus c is a factor, then you know f of c would be 0. That's what it means to be if and only if. It can go both ways in the theorem, okay? If the if-then statement, okay? So, or I shouldn't say the if-then statement, but it's basically equality. That's how we kind of think of it. All right, so let's look at a problem like this. So f of x equals negative 4x cubed plus 5x squared plus 8. And I want to see if x plus 3 is, let's do this. Let me just write x plus 3 and then I'll ask the question. So I want to find out is x plus 3 a factor of negative 4x cubed plus 5x squared plus 8? Do not use long division / synthetic. Okay, so that means we can't use long division, we can't use synthetic. So what we could do is we could say x plus 3 equals 0. So then we know that x equals negative 3. That's my c, right? So we now know my c. So all I have to do to determine if it's a factor, is all I have to do is plug negative 3 into the polynomial. So this will be negative 4 times negative 3 cubed plus 5 times negative 3 squared plus 8. So this will be what, 9, 27. So we got 27 times 4. They're both negative, so we're going to get 108 plus 45 plus 8. So I should get 161, which we do, okay? So then we get 161 as our remainder, right? This is our remainder. F of c has a remainder of 161. So this means by factor theorem, x plus 3 is not a factor since the remainder is not equal to 0. Okay, so that's all you have to do. We didn't have to do long division or anything. Let's try another one. Let me have you guys try this one. So do f of x equals 4x to the 4th minus 15x squared minus 4 for x minus 2. So do the same thing that you did in the last one. Let's determine using the factor theorem and the remainder theorem if f of 2 is in fact x minus 2 is in fact a factor. Okay, so hopefully you guys are back and you did f of positive 2 is equal to 4 times, well, 2 to the 4th is 16 minus 15 times 4 minus 4. So let's see what we get. We should get, let me see, 32, let's see here, 64 minus 60 minus 4, which is 0. So that's my remainder. And we say since the remainder is 0, this is another way we can say it, by factor theorem, x minus 2 must be a factor of f of x, right? So this is, instead of, if somebody just wants to know if something is a factor, then all you have to do is plug in, when you're dealing with polynomials, is all you have to do is plug in whatever they want to find out the factor is, plug in the, when you solve it equal to 0. And if you get 0 as the remainder, it's a factor. If you don't get 0 as a remainder, it's not a factor. That's what the factor theorem tells us, okay? Okay. So here's a note. I think this is a theorem, a polynomial. I don't have it listed as a theorem. I don't know if this book lists as a theorem, but this is a polynomial cannot have more real zeros than its degree. Okay. Okay, so a polynomial cannot have more real zeros than its degree, all right? So what this is basically saying is that if you have a degree 3 polynomial, then it can have no more than 3 real zeros. It might have 3, it might have 1, but it can't have more than 3, okay? So Descartes' rule tells us how to talk about these real zeros, okay? And the number of positive and the number of negative, okay? So this is probably something many of you have not ever used before. This is not a very common thing, probably outside of this class or in much higher levels of math. Rule of signs. Okay, so this is called Descartes' rule of signs. So it says let f be a polynomial. Why am I writing that? F be a polynomial in standard form, and that's the form that I wrote in 4.1. So the theorem says the number of positive real zeros. So now we're talking about the positive real zeros is either the number of variations in the sign of the non-zero coefficient of f of x, or else equals the number less and even integer. Okay, so that's, I'll talk about that in a second. Let me write this other one. The number of negative real zeros, and again, we're talking about real zeros, not imaginary, real zeros of f is either the number of variations in the sign of the non-zero coefficients, just like before, but this time of f of negative x, or else equals that number less and even integer. Okay, so it says the number of negative real zeros of f is either the number of variations in the sign of the non-zero coefficients of f of negative x. So notice this one is f of x and this is negative x. Okay, so if you're trying to determine the number of negative, you use negative x. If you're trying to determine the number of positive, use positive x. So this is kind of really wordy, so let me show you what this means. Okay, so let me just show you. So it says find the real zeros of f of x equals 3x to the 7th minus 4x to the 4th plus 3x cubed plus 2x squared minus x minus 3. Okay, so that's rough. So what we do is we first look at this and we see how many sign changes there were. So I'm going to say number of positive reals. Okay, so what we're going to do is we're going to count the sign changes. Okay, sorry, I just got the hiccups. So we have 3x to the 7th minus 4x to the 4th plus 3x cubed plus 2x squared minus x. So hold on one second. Okay, so it says we're going to count. So this is plus, right? This is minus, this is plus, this is plus, this is minus, this is minus. So what we're going to do is from here to here, that's one sign change. From here to here, that's one sign change. From here to here, that's no sign change. From here to here, that's one sign change. And from here to here, excuse me. You guys, I'm going to have to go grab a drink. Sorry about this. I'm afraid if I pause the video, it's going to boot me out. So I'm just going to go grab a drink to get rid of the hiccups. I'll be right back. Okay, I'm back. Sorry about that, you guys. I just couldn't function with the hiccups. So hopefully you're still not, I didn't mess everything up too much for you, but look at, here's one sign change, two sign changes, three sign changes. So we say that we have three sign changes, but then there's this weird part that says it's the number of variations in sign or else equals that number less than even, okay? So what would be 3 minus an even number? Well, an even integer. Well, it could be 3 minus 2, and 3 minus 2 would be 1. Now, we can't go further because we can't have -1 real zeros. And remember, this is a quantity. This is not saying what zeros are. It's not saying that the 0 is 3 and the 0 is 1. What it's saying is how many positive reals. There's either 3 or there's 1 because I can subtract an even from 3. Now let's do the number of negative real zeros. Okay, but this time I got to do something a little different. I got to plug negative x in. So for this one, I'm going to plug negative x in, and this is going to become 3 negative 3x to the 7th, right? Because if you take negative x to the 7th power, it's going to be negative 3x to the 7th. Now this one will stay negative 4x to the 4th because the 4th power keeps it positive, and a positive times a negative is a negative. This one will become minus 3x cubed. The next one will become 2x squared. The next one will become plus x, and the next one will become minus 3. Okay. So now let's count the sign changes, okay? So from here to here, that's 0 sign changes. From here to here, that's 0 sign changes. From here to here, that's 1. From here to here, that's 0. And from here to here, that's 1. Remember that it's about the variation in sign. So when you go from a negative to a negative, that does not actually count. So we actually have 2 sign changes, 1, 2. So what we're going to do is we're going to say there is 2 real zeros that are negative, or 0, because I could subtract 2 from 2 and get 0 of negative real zeros. Okay, so again, the Karch rule is a little bit strange. I don't think many of you have probably dealt with this too often. Maybe I'm wrong, but it doesn't come up very often. It's a very special thing, a special concept that helps you kind of eliminate the possibilities. So we're just learning it to know it, but it's not gonna, dictate the whole rest of our course or anything like that. Okay, so now let me have you guys try one for the Karch rule. So I'm gonna give you guys f of x equals 5x to the 4th plus 2x squared minus 6x minus 5. Okay, so pause the video and see how many positive real zeros and negative real zeros there could be. Okay, maybe something I should have done, you guys, hopefully you're back from the video. What I should have also done on here is I should have said there are 7 possible real zeros overall, since the degree is 7, right? Right here is a degree 7. Okay, so for this one, let's find out total number of zeros. Let's do positive real zeros. And let's do negative real zeros, okay? So once again, if you guys haven't had a chance, pause the video and come back and let's figure all this out. Okay, so hopefully you came up with total number of zeros is 4 because the degree is 4. And then if we do sign changes, from here to here is no sign change, from here to here is 1 sign change, and from here to here is no sign changes. So that means that we have 1 possible real positive 0, right? Okay, now let's do the negative. So now we have to do f of negative x, and that's going to be 5x to the 4th still. This will be plus 2x to the 4th. Now this one will become plus 6x and then minus 5. So now we count the changes. Positive to positive is nothing. Positive to positive is 0. And then positive to negative is 1 sign change. So we come over here and there's 1. And we can't subtract an even integer from either one of these. So this is just my final answer. This is everything right there. Okay, so hopefully you guys got that. And that's basically the Karch rule. Definitely something I'm going to ask you on the exam. It's just something whether you know how to do it or not. If you paid attention to the video and took good notes, it should be straightforward. Do a few homework problems and you should get it right on the exam. Okay, it's just about knowing the Karch rule. So then we have the rational zeros theorem. Okay, and the rational zeros theorem says if f of x is equal to this polynomial, so this is how I showed you guys in the beginning of how we can write a standard form of a polynomial, where a sub n cannot equal 0, and a sub 0 cannot equal 0. Okay, so it says if p over q is a rational zero of f of x, then p must be a factor of a naught or a sub 0, and q must be a factor of a sub n. Okay, so basically what this means is if you have this fraction p over q and it is a rational zero, it turned out to be a rational zero of f of x, then that tells you that the way that fraction was made, p over q, the p had to be a factor of the last term. So the p goes with the last term, a sub 0, and the q goes with the first term, a sub n. And it goes with the coefficient in the biggest degree, and then the p goes with the constant, okay? So let's see here. Let's take a look at f of x. Let's see, I'll just do one of these just to kind of show you guys. It's kind of nice to just know ahead of time, but at the same time, if you get a whole bunch of lists of p over q's, then you're going to be in a little bit of trouble. So this is how we can use it to our advantage. So that theorem actually tells us that we can do this thing. We can take q and do plus or minus 2 and plus or minus 1, right? Because those are factors of 2. And then over here, for this guy, for our p, we can use plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1. Those are all the factors of 6, okay? So if we want to write our p over q's, we take all the p's, all the possible p's, so that would be, and then we divide them by all the possible q's. So I'm going to just start at the bottom and work to the top, okay? So this will be plus or minus 1 divided by plus or minus 1. But that, you guys know, is going to be plus or minus 1. Then the next one will be plus or minus 2 divided by plus or minus 1, so that's plus or minus 2. Then plus or minus 3 divided by plus or minus 1, and then plus or minus 6 divided by plus or minus 1. However, the next one is divided by 2, right? Because we've already used up this one, so now we got to use up that 2. So now we're going to do the same thing, plus or minus 1 over 2. Let me write it like this. So that would be plus or minus 1/2. And then we do plus or minus 2 over plus or minus 2, but that's already 1. We already did that one. Then let's do plus or minus 3 over 2, so that's plus or minus 3/2. Then we do plus or minus 6 over 2, but 6 over 2 is plus or minus 3, and we already did that one, okay? So this would be our list of all the possible rational zeros. Remember, rational means it can be written as a fraction. So that means like 1/5, 2/3, 5, 7, you know, square root of 4 is 2. So anything that can be written as a fraction, okay, that's a rational zero. Up here, what we were finding, this is talking about real zeros. So it's kind of two different things. All rational numbers are real and all irrational numbers are real. So this is talking about like how we can dictate positive and negative real zero, or not dictate, but find how many. This is trying to help you find out if something's a factor, which means it is a real zero as well once you solve it. And now this is giving you like a list of rational zeros, and rationals are the nicer ones. Like square root of 2 would be an irrational zero, but it still could be a 0. So it is real, but it is not rational, okay? So when you say rational zeros, you basically are saying the nice ones, everything that can be written like nicely, like fractions or something like that. That's not to say there's not anything else out there, but this theorem helps you find a list of rationals. And it's not saying that all of these are the zeros. It's saying this is your list. If it's going to be one, it's going to be one of these. Okay, you know, and some problems don't have rational zeros. They might only have complex or irrational. Okay. So let me have you guys do an actual problem where we want to find all of the rational zeros. Oh no, you know what? Let's find all the real zeros. So this is an actual like test question. Now that we have all this knowledge and all these things we can do, I want to find all the real zeros. Okay, so this is a test question. and must be done like this. Okay, so I'm going to give you guys a specific way I want you to do it. Okay. Obviously, it's not like a cookie cutter, it always works. You do have to, you know, decide certain things, but in general, this is how it should work. Okay, so if I have f of x equals x to the fourth plus x cubed minus 3x squared minus x plus 2, okay? We need a place to start. Now, if we did not have a calculator, I would recommend we do P over Q and see a good place to start with a list. However, we do have a calculator in this class. And so what we're going to do is we are going to use the calculator to find the first possibles or the first zero. So what I'm going to do is I'm going to turn on my calculator. Let's give it a second. Okay. Let's see what happens. And now I'm going to enter in my calculator. I'm going to enter in my calculator x to the fourth plus x cubed minus 3x squared minus x plus 2. And now I'm going to graph it. So you see right here, over there at 1 looks like a really good 0, okay? Or maybe even -1, or maybe even -2. So it really depends on which one you want to try. I guess we could just try, I don't know. Let's try 1, just because it looks like the easiest one, okay? So all I'm going to do is I'm going to do long division, okay? So you guys should all know how to do long division. If x equals 1 is a 0, then that means that x minus 1 equals 0 was a factor, right? That's from the remainder in the, I should say from the factor theorem, okay? So, or actually that's just from x-intercept. Sorry, that's not from the remainder theorem. That's just from the fact that if it's an x-intercept, this is how we could solve for it, okay? And get our factor. So I'm going to do x minus 1 divides into, oops, x to the fourth plus x cubed minus 3x squared minus x plus 2, okay? So now what you do is when you're doing long division with polynomials, you just always ask yourself the question, what does this guy need to become that guy? What do you need to multiply by? So I need to multiply by x cubed, okay? So now I distribute and I get x to the fourth minus x cubed. But remember, whenever you're doing the division algorithm, you do subtract or you subtract, so that changes the sign. So this becomes a minus and then this becomes a plus, okay? That cancels. And now we're left with 2x cubed minus 3x squared. I just brought down a little help right there, okay? Now you ask yourself the question again, what does this guy need to become this, the first term? Well, that needs a 2x squared. So I'm going to say plus 2x squared, okay? So now I'm going to distribute this now. That'll be 2x cubed minus 2x squared. But the moment I draw this bar, I flip the signs, and this will become negative, and that'll become plus. That'll cancel, and then this will become negative x squared. Okay, now we're going to bring down some help. Oops, let me write this in this. Oops, so this will become negative x squared minus x. So now we do the same thing. That's why it's called an algorithm, right? You do the same thing over and over again. Now we say, what does that need to become that? We say minus x. So then this would become, now when I distribute again, right, I'm going to take this minus x times that, that's minus x squared. I take this minus x times that, that's plus x, right? I draw the bar, so that would be plus, and that would become minus. So gone, and this becomes minus 2x squared. Let's bring down some help. Plus 2. Now we ask ourselves the question again. And again, it should be boring and repetitive, but that's the algorithm. That way it makes it so you don't get confused, you don't struggle, because it's kind of like always the same. So then what does an x need to become a minus 2? Oops, not x squared. I'm sorry. This is just a plain old x. That's my mistake. So please fix that. So it needs a minus 2. So then I'm going to put a minus 2 right here. So this will become minus 2x. And when I do minus 2 times a negative 1, I get plus 2. But when I draw the bar, the signs change. And that becomes 0, and that becomes 0, and we get 0. Now, we knew that we should get a remainder of 0 because this was an x-intercept, meaning that you got 0 when you plug this in. So we now have a new polynomial. This is called, oftentimes, and depending on the book, this is called a depressed polynomial, because now it's x cubed plus 2x squared. Oops. X cubed plus 2x squared minus x minus 2. Okay, so now we have this. So we can either try to use another 0 and do long division again, or if we'd like, we could try factoring. So I'm going to try factor by grouping since there's 4 terms, right? I'm going to try factor by grouping. This will become x squared times x plus 2. I'm going to factor the negative out, and this will become x plus 2. Now I notice what is this and this each term have in common, or each piece. Each piece has an x plus 2 in common, so I'm going to factor that out now. Okay, and then this will become x plus 2 times x squared minus 1, right? Because if you divide this by x plus 2 and this by x plus 2, they're going to cancel. This will become 1, and then this will just become x squared. Okay, so now we're here. Now we can factor this, and this becomes x plus 2 times x minus 1 times x plus 1. Now, if it isn't factorable from that point, then you have to do long division or synthetic division from there. But now I can see that my zeros are x plus 2 equals 0, x minus 1, oops, x squared minus 1, x minus 1 equals 0, and x plus 1 equals 0, okay? Now here's the thing, let's clean this up. X equals negative 2, x equals 1, and x equals negative 1. But look right here, we already said that this was one of the zeros from the calculator. So when you did this and you got a remainder of 0, you were saying that x equals 1 is also a 0. So we have 2 of them. So that means that x equals 1 has a multiplicity of 2, okay? So now, if we wanted to factor this, we could. So I found all the zeros, right? So this is all of my zeros, right? There's 3 zeros, 3 distinct zeros. One of them is repeated, okay? So we have negative 2, 1, and negative 1. And then if we go back and look, we have multiplicity of 2 at 1. And look what it did at 1. It bounced off of 1. So we should have known that it had even multiplicity because that's what we learned in 4.1. We should have known that the other two had odd multiplicity for x equals negative 1 and x equals negative 2 because they go through the x-axis. So this is all this information that we're gaining, okay? Also, I now know how to factor. So this is my f of x, right? Well, I have all the factors of it now. I can now say that f of x can be factored as x plus 2, x minus 1 squared, and x plus 1, right? This is the factored form of this, okay? So we actually factored something that we don't know how to factor, okay? There's no factor formula for that. Well, there is, but not in this class. So we now have a factor of a 4th power or 4th degree polynomial that had 5 terms, okay? So we did multiple things with this. We did long division. We got a remainder of 0. We used our calculator to start to find the first 0. So this one I got. So this one right here is from the calculator. So normally for these problems, you'll have to use your calculator to find 1, look for an x-intercept, because that means it's a 0. And then from there, you do long division or synthetic. I like long division better just because it's safer. Synthetics kind of has some hiccups here and there. So I just wanted to go over that. When we do our meeting, please show up to the meeting on the next day of class, because I'll definitely do another one of these if you guys would like. And it'll get you more practice on this. But this is definitely how I want it on the exam. There'll be at least one exam question from this. And we're going to do more of this in 4.3 as well. Okay, one last thing. Well, you know what, I'll cover that in the next video. I'll talk about the intermediate value theorem in the next video. I'm going to end this video for now, guys. Thanks for watching.